people, including consultants and interns, other students that we have. And as many of you know, NASA is now housing one of the D-Wave devices, one of the two D-Wave devices. So basically, the story that I wanted to tell you today is some of the progress that we made thus far in programming the device for applications, and also some efforts in the tunability of the device. I'm going to explain what is that about. So let me just give you a brief overview of what the device is good for. So the device is basically good for solving discrete optimization and machine learning type of problems that can be mapped to this form. So basically what you have here is an objective cost function that you want to minimize. So basically here the variables are this S, and they take values between -1, they take values -1 or +1, so they're spin variables. And what you have is that what you're given is the values of H's and the J's. What we call this data, we're going to call this the local fields and the couplings. So this quadratic expression, what you're after is finding the assignment of each one of these binary variables that minimizes the value of f. So that's basically what that's all what the device is good for. But it turned out actually that this problem in itself is very hard. The problem within the computer science complexity theory is called an NP-hard problem. So there is no, in principle, there is no known algorithm that can solve any realization, an arbitrary realization of this problem in polynomial time, or solve it efficiently. So here is how we go about going from the classical expression. This is completely like a classical quadratic expression that you want to minimize. This is how we go to the quantum, kind of like doing the preparation for the quantum world. So basically, one can prove that if you turn all the S variables into sigma, into poly matrices, sigma set, then in principle, this state vector with the corresponding assignment corresponds to the ground state of this Hamiltonian as well. So notice that everything here, we're talking about the ground state of this particular Hamiltonian. How is that tied? Let me do a crash course in adiabatic quantum computation in one slide. How is that tied to a quantum algorithm that can solve this type of problems? So basically the approach was formulated originally by Nishimori, and in this particular formalism with the transfer field sigma x in 1998. And the idea is the following. The idea is to do a process that is called a quantum annealing. Basically what you do is notice that the HP that I had denoted in the past, it was only containing sigma set type of operators. Here, when you introduce sigma x, basically here you introduce tunneling and quantum fluctuation. So the Hamiltonian is no longer classical, and you have basically a quantum Hamiltonian. The idea behind the approach is you start with you basically start by using the adiabatic theorem of quantum mechanics. And what you start is you initialize your system in the ground state of a Hamiltonian that you know at time equals 0. And you propagate, you tune the knobs of your Hamiltonian in time until you end up in a Hamiltonian that in this case is HP at the running time of the algorithm. So what the adiabatic theorem is telling you is that if you do this in an adiabatic fashion, it's very slowly, then pretty much you maintain in the ground state throughout the evolution. And since we already shown in the previous slide that the ground state of HP is the solution to the problem, then as long as you remain in the ground state, with high certainty, you're going to read out the solution to your problem. So that's the basic strategy of how you do that. So what is our ground state at time equals 0 is basically the ground state of the transfer field. In this case, it would be a full superposition of all the states in the computational basis. So my computational basis here are the eigenstates of sigma set of HP. So basically, as I said, you start with, you blast the transfer field, and then HP is turned off, and then you slowly turn on HP, and you end up in pretty much what you're doing is you're preparing HP, and you're turning off the initial Hamiltonian, the transfer field. So basically, you're turning off all the quantum fluctuations in the system. And then you end up in the resulting state, hopefully, if the process is adiabatic. So let me tell you basically what this talk is about and what this talk is not about. So at NASA, we're interested in applications. And In particular, we're interested in seeing if there could be any enhancement in the performance by applying quantum algorithms to all these hard computational problems at NASA. So this talk is not particular. I mean, I'm not going to discuss at all anything that you've seen in the literature about the debate about if the D-wave is faster or not, what's going on with the benchmarks. But I point you to this reference in particular that I think it has. You can read in this blog and some of the comments. It gives you kind of like a state of the art of what's going on in the benchmarking. So as I mentioned, we're interested in applications, and one of the things that I want you to catch your attention is the significant progress in this field. So when you read about these benchmarks, you see actually that D-Wave is kind of closely competing with one processor, like a desktop type of computer, like an Intel processor. Here, like in this stage, we're actually much way behind. So actually, we're kind of like in the 1940s of computation, where actually we're trying still to implement very small instances of the problems. But actually, what I'm going to talk to you about today is that we managed to implement one of the instances that we think is already compatible with some of the instances that you would find in real-world applications. So you can see the progression. Some of the, for instance, like I was the one who implemented this particular problem where I was in the group of Alana Spurugusik. We only managed to embed a 6 amino acid instance. So pretty much this is something that you can do with paper and pencil. So it's a very trivial instance, but it shows all the steps of how to implement a computational problem into the quantum device. Many of the efforts in the group, like actually people that are present in the audience, you can see that they're working in what they call operational planning, so like scheduling of tasks, navigation type of problems. One of the research assistants that is working with us is doing like solar flare prediction. That's actually Bayesian learning the structure of Bayesian networks. And the one that I'm going to talk today is about the diagnosis of multiple faults in electrical power networks. So one of the things that we want to take this research is to complicate these structures and make it into more realistic electrical networks as the ones that you find, for instance, in the International Space Station. That's some of the things that you wanna catch any faults in the system. So what is common to all these problems, because of the framework I presented in the first two slides, is that you need, regardless of what you do, all these problems need to go at some point to this central equation. That is this quadratic expression in terms of binary variables. So all the research, the first step in this research, and it might take actually a few months, from weeks to months, is actually to understand the problem and map it here before you even think of implementing the device. So this is a collaboration with the Advanced Diagnostics and Prognostics team, this particular part of the research. Let me start with the statement of the problem. So basically, here is a simple realization of the problem. What you have is an electrical network. Each one of the nodes in this network is a circuit breaker, and basically it could be on or off. At the top of the network, you have a power supply, a battery in this case, and the idea is that you are injecting current through the network. The question is, if I give you the readout, let's say from some sensors, some ammeters, at the end of the network, if I give you, for instance, that the readout of this one is low, low, high, high, can you assess what's the status of the network? So in principle, there is a combinatorial number of options that you can try. And the problem becomes even harder if you're not even sure if what you're reading is actually what the status of the network is. For instance, here is where we introduce some binary variables as well for the status of the sensor. So the sensors could be faulty or could be actually in a good shape. So that actually introduces this uncertainty, complicates the problem. Even though it's a tree structure, it complicates the problem significantly by introducing uncertainty in the readouts. So basically, as I mentioned, all these problems need to go back to a quadratic expression involving binary variables. So here is the binary variables that we use. So the natural mapping is for each one of the circuit breakers, you use an X variable. So that's the binary variable that you use. And for each one of the sensors, you also use another binary variables that we label here as Y. The status, the indication, if the variable is 1, then we say that the device is healthy. If it is 0, we say it's faulty. So basically, it's a binary yes/no question. Is it healthy or not? These are parameters as input to the problems, and as I mentioned, they represent the sensor observations. So just to give you a sense of how you construct this type of functions before you go into mapping into the device, is first we start to establishing what's the objective function that you want to minimize. In this case, you want to minimize the number of faults. If we assume that actually the probability of failure is the same for all the devices in the network, the most likable explanation would be the one that minimizes the number of faults. So we want to minimize the number of faults in this problem. And at the same time, something that is very important is that the readouts are consistent with the predictions of the status of the network. So there are two terms that you need to take care of. This particular term, the number of faults, is very trivial in the sense that all that is doing is counting the number of faults. Basically, you can see that whenever any of the variables x or y is 0, you end up with a penalty lambda. So it will increase the energy whenever the variable is 0. If the variable is 1 and is healthy, then this whole term will be 0 all the time. So basically, it's kind of like counting the number of faults in the system. The part of the consistency is a little bit more complicated. And here comes one of the difficulties that we face all the time. And is that to represent this consistent term, for instance, if you want to check if the readout, so basically this term here is checking if the readout and the prediction are in agreement. In order to check this, you need to check the status of all the path from the source all the way down to the emitter. So that's why you have here a polynomial, a multiplication of these variables that is telling you pretty much if this is 1 and this is 1 and this is 1 and this is 1, then the prediction should be 1. The emitter should be 1. And then you compare that with the variable of the input parameter. For instance, basically this function is telling you if the parameter is 1 and the prediction is 1, then this becomes 0. If the emitter is 0 and the prediction is 0, then you also get a 0. So basically, you only get a penalty lambda path whenever they're in disagreement. So that's why it's a consistency term. The interesting part of this is that this involves a polynomial of high degree, because you're multiplying all these variables, and as the depth of the tree keeps increasing, basically what you're doing is raising the degree of this polynomial. Fortunately, we developed some tricks to break this term sufficiently all the way from these high order polynomials to a quadratic expression. So that's the first step in analyzing this type of problem. Basically, you need to construct this cubo expression. That cubo means quadratic and constrained binary optimization. That is precisely an analog expression for the Ising quadratic expression that the device is capable of solving. So pretty much when you're at this stage, you're almost done. But there is another like subtlety, and is that, as you can see, if you represent this expression as a graph, as a network, where each one of the couplings, whenever you find a quadratic term, you draw an edge. So basically what you see is that there is an arbitrary connectivity in this graph. And that's not what you find in the device. Basically what we're going to turn is these logical variables representing the devices into some qubits in the quantum annealing device. So that's not as straightforward, because the device, for instance, might not have a connectivity between variable 1 and variable 17 or something, whatever. So some of the details about this programmability and some of these issues of how to make all the steps, we recently published, it came out this week, a paper on the archive about this particular problem. So this second difficulty that I was telling you that you're almost done is because basically this is the real hardware. This is the real connectivity of the real hardware. What you have is that each one of the nodes, or the nodes in this network is a qubit, and each one of the links is a connection between the qubits. So as long as you have a connection, you can implement each one of these couplings that you want to program in the device. As you can see, there is some kind of needless neighbor type of interactions that prohibits to embed this graph directly. So basically what you do is kind of like a divide and conquer approach, where you replicate the variable that is highly connected, you replicate it throughout the network, and instead of spending 1 qubit for each variable, for example, you can spend 9 qubits for one particular variable. Of course, I mean, there's no free lunch, and that's the price that you pay in order to be able to implement this in the experimental device. So you need to pay a price, and the price is that you need to duplicate some of these variables and call them, all of them, variable number 1 inside the device. So basically, that's why you see variable number 1 is here, is here, is here, is all over the place. And it's basically because it's trying to reach out to all the connections that to make up for this plot. In this particular realization, it required 46 logical qubits in this construction, And when you embed into the hardware, you need to make an experiment with 81 hardware qubits. So you see actually that the price is quite high. Let me tell you a little bit about the results. So for this particular instance, we were comparing with NASA's kind of like state-of-the-art technologies for solving this type of diagnosis problems. And it's called HIVE. It's called the Hybrid Diagnostic Engine. Basically, we picked this particular instance because at this particular size of the tree, we noticed the HIVE was kind of like was exhausting its memory without returning a solution. So that was an interesting point for us to actually try to get it into the device and see if we could actually find a solution with the D-Wave. So we actually did for this particular realization, as you can see here. So basically, this is an instance with 6 faults. As you can see, the crosses represent the electrical components that are faulty. There are 6 in this particular realization that explain the best this experiment. And then basically, so those are the ones with energy 6. When you run the device at different annealing times, you see that you successfully pretty much solve the problem a certain number of times, let's say of the order of 10 or 20 times, when you run the device 50,000 times. So you need to run this many, many times, and that's the probability that you would get. Let's say of the order of 10 in 50,000 runs, annealing runs. This is a low probability, and this is a more interesting example. When you cooked up, when you could actually come up with a realization that is kind of like a needle in a haystack type of realization, in the sense that this is the absolutely only explanation for this particular outcome. Here you can have many explanations for this particular outcome. So there is some degeneracy. When you cooked up this particular instance, then you see that if you run the device with the default settings, not even when you run it 50 million times, you don't manage to find the ground state. So you don't manage to solve this problem. So that was an interesting case for us because, as I mentioned, all these realizations are of the order only of 81 qubits. As I mentioned, the D-Wave device, maybe most of you know, is 509 qubits, the one that we have at NASA. And we are trying to solve instances with 81 qubits, 90 qubits, and we're not finding the solution. So that's something that we need to pay attention to. So we're actually, so that's kind of like what led to the next research that is in this paper that we're preparing, is what can we do to exploit, to get the best out of the device, to program the device at its best. So one of the things that we noticed is that we can play with what we call the embedding parameters. That is basically the couplings, as I'm going to explain in the next slide, is the coupling that you set to make sure that all these variables that you replicated behave the same. So it's a ferromagnetic coupling that is very strong, and you can play with the magnitude of this coupling. So that's one of the parameters you can play with. The other one is something that we call the gauges, and I'm going to explain in the next slide what is it about, both of them. So as I explained the parameter setting, remember, this is just an illustration, a cartoon. Imagine that you have this graph, and then in order to embed in the device, as I explained, you need to replicate the variables. The coupling, the embedding parameter that we call here, is this JF coupling, that is this ferromagnetic coupling that is very strong, usually stronger than any energy state in the system, just to make sure that you don't violate, that all these variables have exactly the same assignment, because they are the same variable. It should behave in that way. So the second parameter that we play with is what we call the gauge selection. And the gauge selection is basically a mathematical trick that the only thing that it's doing is basically changing your convention of your problem. Remember at the beginning I explained that when you set x is equal to 1 is healthy and x equals 0 is faulty. So basically what you're doing is you're reversing your conversion, and just by redefining mathematically your problem. But your problem is not any difficult. So the problem is exactly the same problem. From a mathematical point of view, you're just changing the convention. You have that degree of freedom. That's why it's called a gauge selection. It's not changing your energy landscape at all. Here's an example. The way you do this gauge selection is just by flipping the sign. You flip, you decide which one you want to flip. The spin variable, you flip it from SI into minus SI. So here's a toy example with 2 qubits. You have a local term, one local term like a monomial, and then you have a quadratic term. Applying this gauge where you flip variable 1 but you don't flip variable 2, basically all that you're doing is you're flipping the sign of the first term and you're flipping the sign of the coupling. As I explained, this particular trick from a mathematical point of view is not doing the problem any harm. For instance, if you give this to classical simulated annealing, It won't find any difference in solving. It won't be any difficult. But for the device, it is very interesting because in reality, in the device, you need to implement a coupling with -5, and in the other scenario, you need to implement a coupling with +5. And the fact that there is an asymmetry in the experimental realization, then they can significantly enhance the performance of the device, as we're going to see. So basically, this is just an experimental artifact. So what we came up with is what we call a performance estimator, and it's a strategy to do a quick assessment of what kind of gauge you want to implement in the device. So basically, as I mentioned, it tried to give you, from quick runs in the D-Wave, what are the best parameters that you can program the J couplings and the gauges. And one of the nice features of this type of performance estimator is that it doesn't matter the size of the problem. It doesn't scale with the number of qubits. So it just explodes in the fact that you are using an adiabatic machine. That is, you're trying to aiming for the low energy landscape. So here's an example. I mean, I'm not going to explain in detail all the how it's actually calculated, but let me give you let me just show you that actually works. So the blue line in this plot is the performance estimator. And what you need to keep in mind is that this particular blue curve is calculated from very cheap calculation, so of the order of thousands. The red curve is calculated based on millions of calculations, let's say. So actually, the red curve is trying to assess the real performance of the device from long runs, if you run it many, many times. And this one is trying to assess the performance from very, very quick runs. So actually, you can see that there is a great correlation when you adjust the value of J, and in particular, if you had to pick a value of J, for instance, I would say go for 0.95, that is the highest one in terms of the performance. So, and that actually correlates very nice with long runs, extensive runs. The same happens here. So basically what we generated 100 of these artificial, this mathematical trick of the gauges, you can generate randomly 100 of those. And what the blue curve somehow is helping you to decide if you run the device for many, many long runs, what would be the performance, what would be the top ones that you want to pick. So basically, from the 100 gauges, we're just sorting them by performance estimator, and you see that there is a very nice correlation with the real performance of the device. So the performance estimator in blue is correlating really well with the real performance of the device. The real performance of the device, the gold standard, is the counting the number of ground states, because that's actually the probability of solving the problem. So basically then the strategy that we propose is, if you want to solve a hard problem, then basically what you do is, you do the performance estimator that is very cheap, you do it very quick, and then at the end of the day, from that you select the best configuration of the device for solving that particular problem. You pick, let's say, the top 5, and then you run the real device. You really try hard to actually solve the problem. So let me explain that, showing actually some results. So remember, like the first problem that I showed you, that we managed to nail it down. So actually works also for that problem, and you get an enhancement of the order of 5 times. So you see, like, if you have the default settings of the device, if you compare, you divide the ratio of the number of ground states that you get from the default settings, and you divide that of the number of ground states that you get after selecting the top one from the performance estimator, you see an enhancement of 5. So actually it's worth doing, what is shown is that it's worth doing this performance estimator to enhance the performance of the device. So this is for the problem that we already solved. In this particular one is the one that is very interesting, because what this plot is showing is that pretty much the red dots is based on calculation based on 10 million runs. And as you can see, of course, I mean, as I show you, for the no gauge, for the case of default settings, you get 0 readouts. You don't solve the problem pretty much. And then after doing the performance estimator, out of the top 5, there are a couple of them that actually solve that particular instance of the order of 16 times, for instance, in this particular one. So since we already actually extensively run this one 50 million times, and we didn't see the solution, we can estimate a performance of at least 80 times. So actually, that's this for really hard instance. And the last one, this comes from Sergio Boisov, who is working on this benchmark test. We just wanted to show that it is not only for this particular application, but it works for random problems, for random spin glass type of problems. Basically, you see that also doing the performance estimator also helps. So that's basically, this was a particular instance that was hard for both, for simulated annealing and for classical. That's one of the hard instances that they found out, and he just provided me with this particular problem instance. So let me just conclude the talk here. So basically, I mean, what I wanted to give you is an overview of some of the progress in the group about the different applications that we're working on, and that we're slowly moving, I mean, towards more and more larger and larger realizations by implementing new mathematical tricks and new mappings that we're developing since the first realization of a real problem on the quantum device, all the way to the new instances that we're doing right now. Let me just mention that even though this problem, of course, is not one of the most difficult instances because it's on a tree, we expect that by complicating the complexity of the network, just interconnecting the network a little more, then in principle you can reach, you can, of course, you're going to reduce the number of qubits that you can implement, the number of electrical components that you can implement, but some of the NASA competitions for this particular problem is of the order of 40 to 60, and we're already solving components with 100 components. So I think we can find a middle ground where actually we found an interesting instance in maybe in the next generation of the device with a few thousand qubits. So some other applications that we're working on, I'm working particularly in some problems in origin of life, in biology, from aeronautics, from earth science. So we're extending these approaches to different application domains. From the programmability aspect, I just show you our first efforts to actually understand a little bit what's going on in the device. I mean, the good thing about being at NASA is that we're not competing. I mean, we're not interested in selling, but we're actually interested in seeing if this could be of any use and the potential of the device. So we want to exploit this, and to do that, that's our first stage also of understanding how do we cope with the noise in the device. It's a quantum device. It's been proven, at least for small unit cells of the device. They've shown entanglement. They've shown some coherences. The question is it still a noisy device, and how do we cope with this? And this performance estimator is a first approach to characterize, in principle, any quantum device. So that's what we're going to move next in the next generation of these projects. And it's basically to do a full characterization of the device, characterizing the couplings, and characterizing the values of H, the longitudinal fields as well, trying to understand a little bit the noise, trying to select directed selection or a guided search of this gauge, because at this point, you still need to generate random gauges, and then at the end of the day, pick the best one. So how can you come up with strategies using machine learning that actually allows you to select the best gauge, understanding a little bit of what's going on, learning from the measurements in the device? That's pretty much what we're moving up forward. And just it seems like maybe this talk is a little bit, doesn't touch upon the quantum simulation topic, but I want to emphasize that as you're going to see tomorrow from Vadim's talk, the group is also heavily on the physics of the device. And we're exploring like, not as a simulator, but some quantum tunneling experiments on the device, and also some like statistical physics. David is going to talk tomorrow about the Cherry-Toki-Patty model. So we also dive into the physics of the device, and as Nathan was mentioning, if you understand what's going on with the parameters in your Hamiltonian or in the problem, then you're at risk of not knowing what you're simulating. So basically, that's one of the main difficulties from the tunneling experiments, is try to get to really understand what's the role of the noise and characterize the device really well. So all these strategies that we're developing here, it will impact somehow the next quantum simulations that we do in the device, and also the performance of it. So that kind of like ties together all the projects in the group. So I think that's it. So that's all.
Okay. I have one question. Could you explain which is the difference between a quantum annealer and an adiabatic quantum simulator? Because I don't follow.
Sometimes it's just, I mean, that's still a debate. Well, the way I see it is a quantum annealing. Adiabatic quantum computation was introduced by Farhi in the 2000. I'm not sure, I haven't talked to him if he was aware of Nishimori's paper. But in principle, adiabatic quantum computation relies heavily on the adiabatic theorem, and you try to remain in the ground state. For a quantum annealing schedule, it's more flexible in the sense that you can have a device at room temperature. You might actually just ramp it up and maybe try to escape from the ground state and then let the system relax because it's an open system. So basically, the distinction that I make is that quantum annealing is more general, more like noisy, realistic conditions. Adiabatic quantum computation is usually kind of like a zero temperature, fully coherent type of realization.
The quantum annealing has entanglement and coherence.
That's something that actually, there is a paper, I think it was a PRX paper recently, a few weeks ago from Dewey, showing that there was entanglement in quantum annealing in the device under the noisy conditions. So that's a paper that came out recently from the Dewey people.
Yeah, can you go back please to slide number 2?
To 2?
Yes. I think it was 2.
The first one? This one?
That was kind of
Sorry. This one? This is slide 2.
yes. Sorry, still have a good memory.
Mhm.
So, how did you go from the real world classical data function space into the Hamiltonian? How did you map that? You glance on that quickly.
Yeah. So basically, as you can see, like from an operational point of view, what you do is you replace the S. There is nothing but just a replacement of the S by the sigma set.
So you put it as it is?
Yeah. So if you do it identical, the only thing that you replace is the S by the sigma set. And what you can see that works is because basically when you apply sigma set to any, let's say that actually you apply it on the solution. You apply HP to the solution, to the CAD. You can do this exercise. Apply HP to sigma G, and you will see that you will get an eigenvalue that is the ground state of the energy of this particular assignment.
Is that because S is binary?
It's because all these states, each one of these assignments are basically the eigenstates of these operators. So anytime that you apply any component of this H on this one, basically you're picking SI. So that's basically, so when you apply sigma I set on this state, basically you pick up SI, the same state. So it's an eigenstate, which you can show is an simple exercise, is that this particular state is an eigenstate of HP with the same energy. And it maps 1 to 1. So that's just a 1 to 1.
So your performance estimator seemed really interesting. It seems like you have kind of a fast way to figure out which gauges are right.
Exactly.
And that correlates. So what's that performance estimator? Did you explain that? Maybe I missed it.
I didn't explain it.
Okay, how does that work roughly?
So basically what you do is, that's why you saw it is a pilot. So basically what you do, and as I said, the intuition behind is that if the device, the intuition that it gives you is that if the device is in reality a quantum annealer and is trying to go for the ground state energy spectrum, if you run the device with the different settings and you put them on a track, let's say that you run it 10,000 times, short runs for each one of these different settings. You run all of them with the same 10,000 times.
Yeah.
If you look at the energy, you sort the energy, let's say that you read out 10,000 times, then you have 10,000 times, 10,000 states that you can sort in energy. And if you look at the energy of the elite, of the kind of the elite runners that are coming out of the device, then in principle, it gives you a sense of which one is solving the problem better.
Right.
Which configuration. It's kind of like it's an elite mean over the top runners. So the next stage that we're going to do, as I said, is the next stage that we're doing right now is we're not even going to rely on experimental runs, but we're going to do a heavy experimental runs at the beginning, characterize the device really well with machine learning. And then from that, you can predict if the gauge is good or bad without doing these quick runs. So it's kind of like to bypass the experimental runs altogether.
Okay.
But of course, I mean, there is a first very expensive state that is using the machine learning to characterize the device in the first place.
So you kind of explore the parameter space with a bunch of things and then kind of figure out what would the optimal thing be
what was
to
the
do.
optimal? So basically, you kind of like put them to compete in the same tracks with the same problem, the same settings, and you see which one is. Just take a quick pick to the lowest energies. That's basically what it's doing.
So there's this kind of machine learning on the DREG machine, not with. Yeah. Okay.
It's not there yet, but I think the next step that we're doing is actually we're going to use some of this.
Just a quick question. What sort of meta heuristics were you thinking about for applying the machine learning to the DWAG system?
So basically, the standard thing that we can do right away is kind of like use, the first stage that we're going to do is to characterize the J couplings. Basically, you can use kind of like, for the first stage is unsupervised learning, just regular clustering, just to see, just trying to understand from generating many gauges and trying to see which ones are the features of a good gauge or a bad gauge. And from there, you can, when a new gauge comes into place, then you can classify into either a good result or a bad result. So just standard unsupervised, supervised learning, because you need to have some examples that you know that is performing well. So basically standard supervised and unsupervised learning.
So run it through DB scan and then do nearest neighbor set.
Yeah, so basically what we take is, we try to encompass all the couplings, all the nearest neighbor couplings and characterize them.
Let's thank speaker again. The next speaker is Nathaniel. He's going to be from computational university of the Fermi-Hubbard Hamiltonian.
Okay, thanks to the organizers for inviting me. And I'll be arguing for this statement, that the Fermi-Hubbard model is a universal for quantum computation. And I'll be talking about it in the context of multi-particle quantum walks. And I worked on this with collaborators Ning Bao, Patrick Hayden, and Ron Salton, who are here today. So I'll give a brief motivation for why this might be interesting. First of all, the Fermi-Hubbard model has at least two interesting characteristics. It's the simplest theory of interacting fermions in a graph, and by simplest here I mean not easiest to solve by any means, but simplest in terms of it's one of the simplest additions to a Hamiltonian you could have beyond a free hopping model, and in a model's interesting systems such as high temperature superconductors. And then the other thing is that the universality shows that the simulation of any sort of Fermi-Hubbard system is as difficult as it could be in some sense. And then, of course, it would also be interesting to experimentally construct something like this, but I'll leave that for later. So first, I'll just put up the Fermi-Hubbard Hamiltonian and explain it briefly. So there's a kinetic term, which is just like a type binding model. It's a hopping sort of term, and then there's this U parameter, which is like a Coulomb interaction with zero range. It's a penalty for two fermions being on the exact same site, and we're going to be interested. We'll find that the limit that's easiest to work with is the limit where U, this parameter that controls the Coulomb interaction, is very large, and this allows us to transform the Hamiltonian into another form, which is called the TJ model. And this is the form that I'll be primarily working with. So the TJ model is we first take the large U limit and then look at the Fermi-Hubbard Hamiltonian below half filling, meaning that holes in the Fermi-Hubbard model are going to be equivalent to particles in the TJ model. And so I'll represent with these A operators. And I'll point out that we're going to be looking at this perturbatively, where the strength of the TJ interaction is going to get smaller as the U parameter in the Fermi-Hubbard model gets bigger. And so that's as I said, the limit that we're going to be interested in. And I'll also point out that there's this extra projection that we do on either side of the Hamiltonian that basically disallows having two particles in the same site. I'll just mention this in passing. And basically the idea is that if you have two particles, if you were to have two particles in the TJ model on the same site, that would be equivalent to having something like -1 particles in the Fermi-Hubbard model on a site, and we obviously don't want that, so we sort of explicitly eliminate that. So there are sort of two inspirations that we had for this, two sort of main papers that we drew ideas from, or sort of technologies from, and combined them to in a new way to give us this result. And so the first is this idea of universal computation by multi-particle quantum walk by Andrew Childs et al. And one of the main ideas that we got from this is basically in this paper they explained that the Bose-Hubbard model is universal for quantum computation, but we're interested in the Fermi-Hubbard model, which we think is perhaps more sort of relevant for many physical systems. And this other paper, which by DiVincenzo et al. And so I'll describe the sort of basic ideas that we use from these papers. The first is that this idea of multi-particle quantum walk. And so just to summarize this briefly, the idea is that you encode your initial state in these wave packets that are coming in on the left, and then through some complicated graph that you've constructed in the middle, you implement your quantum computation. And this graph will contain all sorts of widgets and little motifs that you use throughout the graph to accomplish certain types of gates. And then your output is somehow encoded in is encoded in these outgoing packets coming out of this graph. And so, as I said before, that Childs et al. Studied the Bose-Hubbard model, but their techniques don't apply in the case that we're interested in the case of anti-commuting spin-1/2 particles. We can point out that they do study anti-commuting scalar particles, but it still isn't enough to get the result that we want for where we have spins moving on these graphs. So that's the Childs et al. Paper, and the main ideas that we took from it. The other paper is the DiVincenzo paper, where we're using their key idea of encoding their logical qubits into these three well, first of all, I'll point out that, so just let me back up. There's they're using a time-dependent Heisenberg model, where basically they're achieving their quantum computation by turning on interactions between different spins and then turning them off. And we're going to be interested in what we think is a simpler time-independent model, which is what's achieved by the multi-particle quantum walk. So they encode their qubits into where you have 3 spins denoting each qubit, and this enables them to use only a single interaction to achieve both, to perform both 1 qubit unitaries and universal 2 qubit unitaries. And so yeah, I'll just point, as I pointed out, they use a controlled interaction. We're going to want to avoid that. And so this is essentially what their scheme looks like. Is by these arrows here, I mean applying, turning on these JIJs for two neighboring particles, or 2 neighboring spins, excuse me, for a particular time, tau 1, tau 2, tau 3, etc. And so you can use, if this is the case for where they keep the graph, where they keep their scheme entirely planar, which is something that we are going to want to continue. But you can pick different values of this to achieve any arbitrary 1 qubit gate, and then they calculate particular values that enable them to perform a C0 gate between 2 unitaries, and these values are calculated just for particular precision. And this gives you a universal. So I'll just summarize. So I mentioned 4 models so far. I'll just sort of briefly summarize what their relationships between them. So the first thing that we're primarily interested in is the Fermi-Hubbard model, and we take the large U limit of this to get this TJ model, and then we're using ideas from papers that are focused on these 2 other models, the Bose-Hubbard model and the controlled Heisenberg model, the time-dependent Heisenberg model. And we're sort of generally the ideas that we're using from related to the Bose-Hubbard model are going to be the fact that we're going to have hopping between different terms. It's not sort of static like in the Heisenberg model, and also this idea of having a graph structure on which we're performing a multi-particle quantum walk, and then also the idea that we're going to sort of turn on and off spin interactions based. Which is useful because of how we encode these qubits. We're sort of using this technology from the DiVincenzo et al. Paper, and so I'll describe in the next slides how we bring these ideas together. Does anyone have any questions so far? Let me know along the way. So I'll describe the architecture that we'll be using. It basically just has 3 simple components. There's the simplest of conceivable component, just one particle propagation zones where we're having just single particles move along 1D, approximately 1D lattices. We're using these momentum switches, which we use to push particles of different momenta one way or the other, and this is how we'll sort of push different wave packets together in order to interact them. And we'll be interacting them in these sort of 2 particle interaction zones where we'll be bringing in particles from the left. They're interacting and then exiting on the right here. So that's sort of the basic thing that we're working toward, and then we'll put a bunch of these together and create a universal scheme. So that's the basic outline. So I'll just go through each of these one by one. So the one particle Hamiltonian is very simple. When you're just looking at the one particle subspace, the original TJ model Hamiltonian becomes it's no longer interacting, and all you have to worry about is basically the Hamiltonian boils down to the adjacency matrix for the graph that you're interested in. So this becomes a simpler problem to solve, and basically it just becomes a straightforward eigenvalue problem. And the simplest possible case, you just get plane waves. Particle propagation zones. The more interesting case is where we have we're looking at these momentum switches. So we're attaching, the idea is that we're attaching semi-infinite lines onto each of these open nodes here, and we'll be sending in plane waves from one side and having them go out either 1 or 2, for instance. We're sending them in from one of these and having them go out the third one, and this also boils down to an eigenvalue problem, which I won't go into the details of it, but is straightforward.
And those are the controls?
Sorry?
The semi-infinite things, the waves coming in the semi-infinite chains are the controls that are controlling the interactions?
I think the way to think about it is that the information is encoded on in these wave packets, and we're just using these to sort of bring to interact the spins that we want to interact in sort of a way that we want to interact them. So it's not as much a control as just a means of sort of interacting these 2 spins in the same place, but not interacting spins that we don't want to interact. That's there. So maybe this will be. So yeah, so this is sort of the general idea that we pick the 2 momenta that happen to work for this particular little gadget is pi over 4 and pi over 2 in units of the lattice spacing, and so basically they're directed as follows with perfect transmission. And so I'll just point that out on this slide, or emphasize this on this slide, that this is the magnitude of the transmission. I've just applied the magnitude of the transmission through this gadget, and you can see that things coming from node 1 go through with perfect transmission at this specific momentum and no other, and then things coming through at node 2 will have perfect transmission at that specific momentum at 5, 4, 5, 2. And so we'll use this to our advantage. So now turning to the question of having just a single line like before, except having 2 wave packets colliding. This is sort of the main. This is the meat of the useful. This is the most important part in some sense. This is where we get the unentangling unitary, which is sort of the basis of our scheme. And basically, the idea is that if you're scattering 2 wave packets, you pick up a phase in the singlet part of the spin subspace, and this controlled phase type operation it turns out that we can just use this single unitary to be universal for the scheme. And so basically, and this is just a plot where we're varying J on this axis, which remember is the strength of the interaction term for the TJ model. and it's inversely proportional to U, the strength of the Fermi-Hubbard model interaction term. We're varying this J and seeing how the phase varies, basically asymptotes to negative pi over 4. So this is, so starting to put all these components together, this is what it'll look like. We have wave packets incoming from the left, and we use these momentum switches to direct them at each other and not have any component of it sort of pass through initially, and they interact. And then we're going to go on their merry way to the next such interaction that can occur down the line. So we use 2 of these. We're generally going to use 2 of these in a row for the simple, for the sort of straightforward reason that we have 2 different speed limits in some sense going on these different rails or wires, and we're going to want to make components such that this is an invariant of our sort of gate block for fundamental units, so that if you have, a fast wave packet coming in on the top rail, then it's also going out on the top rail. And similarly, if it's coming in on the bottom rail, then the fast one is also going out on the bottom rail. And just to correct for timing issues, we'll have to add some extra nodes in there to make everything work out properly. And so the important thing about this is that the unitary is in fact universal. And the basic idea is that is the same as in the DiVincenzo et al. Paper, where because this unitary that we've constructed, because of the nature of the interaction in the TJ model. Oh, sorry, did you have a question?
Yeah, I was just got a question. What kind of headaches do you have to face to combat dispersion in the wave packets when they interact?
Yeah, so I'll touch on that briefly at the end. Yeah, it is. That's actually where the bulk of the analysis is, and fortunately, Andrew Childs and his collaborators have. We can almost directly use it.
Complexity that they get.
Yeah. So, but we're optimistic that is very conservative. But so I'll touch on that at the end. Yeah. So basically our unitary is universal because it's of the same spin-spin type interaction that DiVincenzo et al. Are using in their Heisenberg model, the controlled Heisenberg model setup. And our idea is to just essentially, we can approximate this unitary, except for a set of measure 0 or something like that for the different phase values. We can approximate their controlled phase by applying our unitary a number of times. Basically, this sort of block many times to approximate the values that we saw in the previous slide for either their arbitrary for any given 1 qubit unitary or for their C naught gates, and so by the same logic, then this scheme should also be universal. So just to give a flavor of what this would look like, this could be a sort of subset of a graph that we would be performing this quantum walk on, where we have each of our spins initialized in different quantum states in the bottom, and we have wave packets that are moving up through this network and having them interact at different points. And instead of the analogy is to having sort of controlled spin-spin interactions like in the Heisenberg model, except we're sort of discretizing it in some sense. We're having lots of little unitaries that are accomplishing the same idea. And I'll also point out that we sort of I'll just remind everyone that we're thinking about 3 spins as encoding a single qubit, and that's what enables us to use only 1 unitary and have it be universal. And then just as a sort of application of this, we can simulate the constant coupling Heisenberg model as a sort of specific example of this. The previous slide was simulating an arbitrary time dragging coupling, but this is just the example of simulating a constant coupling Heisenberg model, where we're just letting these spins run through and sort of, I guess this is equivalent to trotterizing the Heisenberg Hamiltonian, and over discrete time steps. And so I'll briefly comment on Nathan's question about making these wave packets of finite length, because it would be very disappointing if you had to use exponentially long wave packets or something like that, because that would you want this sort of construction to be sort of polynomial in the number of qubits and gates that you have. Otherwise, it's not very useful. So in order to make these, so this is actually requires a very substantial analysis, but I'm not going to get into that besides just sort of alluding to it. And so everything I've presented so far is just in terms of plane waves, but basically you can make the error between the operation that we want to perform and the actual output of this multi-particle quantum block. We can make this error arbitrarily small if we choose the length of this wave packet to be this kind of extremely large polynomial, but still polynomial value where we have n to the 12th, g to the 4th, n qubits and q gates. But we're optimistic that this bound could be reduced because we go through the analysis in their paper. They make sort of every conservative decision that is possible to make, I think, and I think it's fair to say. And so because this was sort of our work and their work are both sort of more theoretically oriented, just showing that this is in fact possible, that it would be sort of up to the next round to improve this and make it more realistic or useful. So, and I'll sort of end on that note that maybe questions that we could ask in the future are could we make this bound better? Which is sort of I think a prerequisite for any of the future steps you might want to take. And then asking the question, how widely can we generalize this? We've sort of along the way of proving this result have generalized to a number of sort of related systems like anisotropic systems and the TJ model without those little projectors on the side and things along those lines. And we think that this is, in fact, a very sort of potentially very general setup, so that we could use as architecture for other sorts of scenarios. Like, for instance, in the Child et al. Paper, they use nearest neighbor interactions, and it seems entirely possible that next to nearest, presumably next to nearest interactions and all sorts of other, the whole variety of interactions would also be amenable to this sort of analysis. And then the final question, which I'm sure many people here are better poised to answer, better able to answer than I, is that is it conceivable that this could be experimentally useful? I mean, I'm aware that there are experiments that implement other types of quantum walks, and is this sort of completely a pipe dream, or is this something that we could that would actually be thought about in the next few years? So, and that's what I have. So thanks for listening.
Yeah. Concerning the universality of the two-qubit gates, in principle, almost any entangling two-qubit gates is universal if you add some local gates. What's the point of making this new universal?
I guess just because it's a useful result to know for sure, and having the literature, we're hoping to write it up in for the next few weeks.
And do you know any physical setup that may produce that?
So, what do you mean?
Do you know any physical setup that can implement that in an efficient manner?
That can implement
a physical platform that can implement your
the quantum Fermi-Hubbard.
Do you know an actual Fermi-Hubbard model that's existing nearby?
I think he said that probably in the future we could see that.
Yeah, no, I guess the short answer is I didn't have a specific implementation of the Fermi-Hubbard model in mind, but it's meant to be a general.
You can just have an optical lattice with fermions located in optical lattice.
Yeah, I mean, that would be an example.
A quick question.
Sure.
So we know that this complexity analysis holds for both bosons and fermions. So I'm curious, do you imagine that the same results would hold conceptually for anyons?
That's a good question.
That's a good question.
All right, I consider my question answered. Thank you.
You know, I understood how the U that you wrote down kind of looks like a control Z gate. So it kind of looks like a 2-qubit interaction. But to be universal, you need to have the single qubit rotations too, gates too. And maybe I missed that in your talk.
Yeah, so I should.
Is that kind of a trivial thing, so you didn't mention it, or?
No, I should probably emphasize that again. Let's see.
I'm sorry if I missed it. But.
No, it's an important point. Basically, the idea is that because we're encoding these a logical qubit over 3 spins, then we can sort of internally manipulate.
Okay.
Using the
So yeah, so those are the internal manipulations. Okay,
yeah.
I understand.
Yeah.
Thank you.
Is the minimum number of walkers different in the 2 cases, the Bose versus Fermi?
No, I don't think so.
Is it 3? Do you need 3 for universality? Or is it 2?
I guess maybe I'm not sure what you mean by minimum number of walkers.
So in the child result, there's some statement that you need like I think 3 walkers before you get universality. Is that correct, or am I?
So well, I guess it would have to be at least that, because we need 3 just to implement a single qubit. So,
in your case,
yeah,
right.
Yeah. Yeah. So.
Question?
So to answer your question specifically, for us we would need at least 6, because we would need at least 3 walkers to implement the 1 qubit unitary. We would need, as you can probably see, 2 sets of 3 to implement a 2 qubit. Just to have anything interesting going on, you need at least 6.
Okay, so let's not speak again.
Things like